What we have here is a pretty standard exponential word problem that we're going to try to solve using logarithms. So we talk about a population and how it's growing, and the first thing it's asking for is its continuous growth rate. Let's do a couple of things here to set ourselves up. Let's talk about t as years since 1990. Since we're dealing with the word continuous in the first problem here, let's go with a formula of the form Q equals A e to the kt. And what we're going to try and do is figure out what we know and what we don't know. Let's think about the A first. That's where we're starting. Well, we actually have a starting value right there, so we know an A. Nothing in the problem is talking about a rate. In fact, that's what we're trying to solve for, so I don't know that. Arg. But let's see if we can plug in a bunch of other stuff. I'm going to start with the right-hand side. We know 18, E, K we don't know, but we do have a time value. We know we're going from 1990 to 2005. That's 15 years. And we do have an output value. We know that we're supposed to be equal to 21.5 at that time. Cool, I know everything except for K. Solve for K. Okay, this is standard 19, and you know how to do it. First thing we're going to do is we're going to divide by 18. E to the 15k, I like to write it in that order, is 21.5 divided by 18. I'm going to leave it like that. I'm going to take the natural log of both sides. Natural log, take the natural log of both sides. Great, we have cancellation. Boom! What we have over here is 15k. So that means k is 1/15 of the natural log of 21.5 divided by 18. And now, this is when I plug everything into my calculator. So to 4 decimal places, what I got was 0.118. Or, as a percentage growth, 1.18% continuous growth. It's a nice check that this is positive, because if it were negative, that would mean decay. So cool, we have a continuous growth rate. Let's move to number 2, and let's do the annual growth rate. Now, what I could do is I could say, all right, Q is now going to be A B to the T. I could plug everything in. 21.5 equals 18 B to the 15 and solve for B. You can do this, but instead I'm going to show you the shortcut. Shortcut. We already have a formula for Q. Q is 18 e to the point 0.118 t. There's an easy way we can take what we have here and convert it into this format. And to do that, we focus in on this piece right here. That's our B. So our formula is that e to the k is equal to b. So if right now in your calculator you compute what that is, what you're going to get is 18 times 1.0119 to the 10th power. And I got that by just plugging this number into my calculator. Yay, we can find our r. Remember, b equals 1 plus r. So r equals 1.19. Percent. Sorry, should have written that as a decimal first. R equals 0.0119, or that is a percent. And that is annual growth. Now, just a note here, note that this is just slightly higher than our continuous growth rate because continuous growth rate happens all throughout the year, and so at the end of the year, you get a little bit more growth. All right, last part of the problem, 3. Okay, in 3, we want to find the time it takes the population to triple in size. So to do this, we can use either one of the two formulas we have. I'll go with the E, since I think it works a little bit more nicely. We have this formula. Note that we're looking for time, so I've got to find my t-value. It takes the population to triple in size. So if I started in 18, what that means is I want 3 times 18 as my ending population. So here's start, and there's end. Now you could just multiply this out, but why? We're going to divide both sides by 18. In that case, the 18s are going to cancel. Natural log of both sides. Here we go. Boom! Canceled. And now to solve for t, we're dividing. So t is going to be the natural log of 3 divided by 0.0118. I didn't do that in my calculator. What does that equal to? Well, I'm getting about just over 93 years. So about 93.10 years. And again, I'm looking for plausibility. If this was a really small positive number, that would be bad. If this was like 2,000, that would probably also be bad. And so I'm really glad it's not negative. So that seems to work. So what we've done here is gone through the steps of solving an exponential word problem using logarithms.